Okay, so good afternoon, everybody. So it's a great pleasure to have Martial Duchamp with us this afternoon. So Martial has joined NTU and MSc in 2016. And before that, Martial Duchamp has obtained his PhD from EPFL in Switzerland on the study of mechanical and electrical properties of 1D materials such as ZnO, nanowires, or CNTS. He then pursued a postdoctoral fellowship at DTU in Copenhagen in the Center of Electron Nanoscopy. During his first postdoctoral contract, he developed innovative approach to measure low concentration of dopant in the context of thin-film solar cell using TEM techniques. He then moved to the Ernst Kospa Center for Microscopy and Spectroscopy with Electrons in Germany, where he pursued his research using unique aberration-corrected TMS. As he shown in his list of publications, he worked in a broad range of subjects, either material science or instrumentation, development-related topics, and he joined MSc, as I say, in 2016. So, Martial, thank you for being with us. The floor is yours.
Hi, everybody. Thank you, David, for the introduction, and thank you, everybody, for joining. So I hope the sound is correct. You can all hear me. So today I will be talking about TEM imaging and mainly, if not only, of in situ imaging of beam-sensitive materials, as well as operando TEM imaging, and manipulations of ferroelectric and ferromagnetic domains. So I will come back to these few points during the presentation. This is my outline. So I will first start to introduce the facilities that are available at NTU and particularly at MSc. Then I will present which type of high resolution imaging we can do at cryogenic temperature and what it is useful for, or how do we use this type of imaging to solve a material science problem. And then I will present in situ and operando experiments at different temperatures, and also when device are exposed to different electrical or current flow. And I will focus on ferroelectric and ferromagnetic structures, as previously said. So let's start with the facilities that I have been using. So I'm using the facility of FACS, which is Facility for Analysis, Characterization, Testing, and Simulation. This facility is located on the MSc building in building N4.1 and in the ABN building. On the top image, you can see the entrance of the building of the facility in the building N4.1. In this part of FACS, we mainly have SEMs and X-rays instruments. And on the new building, which is shown on the bottom image, we have the TEMs, and this new part of FACS has been built recently, and it's open since about 3 to 4 years. What is special about FACS, or what are the high-end instrumentation that we have? So on this slide, you can see that we have ARM200, which is aberration corrected. This is the first aberration corrected TEM that we had in NTU. So what is a TEM, and what is why do we need aberration correction, and why is it so special? Because until the late 90s, the TEM the resolution of the TEM was limited by the spherical aberration of the TEM, and so people were not able to do atomic imaging because of the limit in aberrations. And in the late 90s, people have developed some aberration corrector, which has allowed to increase the maximum resolutions that the TEM can achieve. And by using this aberration corrector, we can now probe individual atomic columns. And on top of that, due to the stability of the microscopes, We can also make some elemental maps. So as you can see on the left-hand side, you have on the bottom left, you have the TM or STEM image, and then you have the different elemental map of strontium and titanium. So we can know which elements are where and what is the amount of each element at atomic scale. We have two ways to use a TEM. So this AM200 TEM is mainly used in STEM mode. It means that you take your electron probe and you focus it to a small point, and then you scan your probe across your specimen and you record the signal for each probe position. So in that case, it's really important to have this probe as small as possible. So you need to have an aberration corrector in the condenser system, which is located in this area on the microscope. And then below you put your specimen, and then you image your specimen. We have a second TM, which is a bit more complex and it's kind of taller. So to give you an idea, the height of this microscope, it's about 5 meter height. So it's a AM300 microscope. So it means that we use it at higher electron energies. And this one is double corrected. It means that we have a probe corrector. So before the specimen, so we can also focus the TEM beam to a really sub-antrum in diameter beam to do some STEM imaging. But we also have image corrector. So it means we can have some plane wave illumination going through your specimen, and we can look at the modulation of the wave where it's going through the specimen, and then record the plane wave image. So we can do both in this type of advanced TEM. It has basically all the options that you may need to do TEM characterization. You can do some spectroscopic imaging. You can do some electron energy loss spectroscopy. You can do some electron holography. It means that you can both record the change in amplitude and the change in phase of the wave when the wave is coming through the specimen. And most of the results that I'm going to present today has been realized using this TEM. So on top of simple TEM imaging, I want to present results that we obtain in situ and operando microscopy. So what does in situ and operando means? In situ means that you apply some stimuli to your sample when you look at it when the specimen is inside the TEM. So the easiest stimuli that has been applied in the past is really to change the temperature of the specimen and look at the phase transformation from the low temperature phase to the high temperature phase. So it's what we call in situ. There are also some other in situ experiments that you can do, typically by putting some gas or introducing some liquid and see how the material react in the presence of different gas or different liquid. And what we call operando, it's really when we operate a device inside the TEM. So typical examples that I'm working on, it's a battery material. So we try to operate the battery inside the material and we see what are the microstructures change that happen when you operate the battery. Or we also do that on a fuel cell. So we can run the fuel cell inside your TEM and you look at the microstructure evolution upon the number of cycles. I do work quite a lot on solar cell and LEDs, even though I will not be talking about solar cell and LEDs in this talk today. And I will mainly focus on the last part of my talk will be on ferroelectric and ferromagnetism. And so the aim of these two studies was really to study the domain wall motion when the device are exposed to external electric field or external magnetic field or spin current, and so on and so forth. I will come back to this point later on. So to be able to do in situ and operando TEM, you need to be able to apply some stimuli on your specimen. And just to give you a flavor on the setup that we have to use, which also imply what are the limitations on sample preparation, I want to introduce the TEM holders that we have used for most of the study. So this TEM holder is quite special because it does allow in the same time to go down to about 100 Kelvin, to apply some electrical stimuli and to control the temperature. At the tip of the holder, which is shown on the right-hand side on the holder, it's where you put your specimen and where the electron beams is going through the specimen. and where the electron beam interact with your material. And then the rod is about 25 centimeters long. And from the black part, it's all outside of the specimen, where you can apply the electrical connections, or you can put a nitrogen dewar below the holder to cool it down. What is very special about this holder is that the cold is transferred from the nitrogen dewar outside of the TM, goes through the rod of the holder up to the tip of the holder when the tip of the holder is cooled down. And you can see in the insert a magnified view of the tip of the holder. And there is an active heater element between the tip and the rod of the holder, which makes sure that the holder stay at the temperature of the microscope, while the tip of the holder is cooled down to liquid nitrogen temperature. And by having this active element, you don't have any heat transfer between the tip and the rod of the holder, which keeps, which makes the holder much more stable as what it would be if we didn't have this active element. And the sample has to be put on a MEMS chip, which is at the end of the holder. So the MEMS chip, it's a piece of silicon, which is about 1 centimeter by 3 millimeter large. And the middle of the chip, you can see a dot, and the dot is where the chip is electron transparent, so that's the area where we do the observation. And 6 needles are connected to the MEMS chip, and we use this 6 needle to apply electrical current or electrical field, and also to locally control the temperature of the specimen. At the time, like 4 or 5 years ago, it was a unique TEM holder that was not available anywhere else. And now it starts to have something like maybe 3 to 4 of such a holder worldwide. So it's still quite a unique instrumentation. We have been able to obtain a sub-Antron resolution at 100 Kelvin. And on the top right image, you can see a magnified image of the MEMS chip. The omega shape lines, that's lines that are used to control the temperature. We pass electrical current through the lines, and we can control the temperature by Joule effect. And the red arrow points where we had to place TEM lamella, and I will come back to that in a few slides. So after the introduction of this holder, let's look at what we can get and what are the type of experiment that we can do using this dedicated holder. So the MEMS chips has been introduced like a bit more than 10 years ago now. And it was really a revolution at the time to perform in situ TM experiment, because it really allowed to have a great stability at elevated temperature. And since this time, people have been able to record images at high temperature, in that case at 700 Kelvin, and they could see the atomic growth of planes inside the platinum particle step by step. So you can really see the evolution of the atomic layer at elevated, and the reconstruction of this layer at elevated temperature, something that was not possible before. So we do use the same technology in our holder, but instead of focusing on the high temperature range, we now try to go in the lower temperature range to study some different phenomena. First, I will start with LNMO cathode material, which is used which could be used on lithium-ion batteries that we have on our portable devices. So I guess you are all familiar with what is a lithium-ion battery, but just I will quickly describe in a few words. So in liquid ion batteries that are used in electronic devices, so you have an anode, usually it's made of graphite, you have a liquid electrolyte, and then you have a cathode material, which can be LNMO or other materials. And when you charge and discharge your battery, you move your lithium ions from left to right or from right to left, depending if you charge or discharge. And so when you are in the discharge state, so on the bottom side you have IV curve. When you are in the discharge state, you have the lithium ion, which are in the middle of this diamond, which are in the cathode material. And when you charge your materials, the lithium ions go from the cathode into the anode, and then the atomic positions where the lithium ions were are left empty in the cathode material. So if this process is fully reversible, the lifetime of your battery should be infinite and they should not degrade. But we all know that with time, the battery degrades relatively quickly, and we want to understand better why this degradation happens. So we want to follow the structure at different state of charge and at different number of cycles to see what are the degradation mechanisms that happen when you operate a battery. Some years ago in 2017, Gao have shown that when you use lithium manganese oxide material and when you expose this material to electron irradiation, you go from the spinel structure, which is the structure that you want to have in your battery material, to the rock-salt structure. And the rock-salt structure is the same as the spinel, but instead of having two lithium ions in the middle of the diamond, you have manganese ion or manganese column in that case. And then you can imagine that when you have a manganese where the lithium ions are supposed to be, then the lithium cannot come back into the atomic position, and then you cannot charge or discharge your battery. So we want to follow basically this specific position and see how it degrades with a number of cycles. We did some simulation of the possible structures that can be found in LNMO. So we have the spinel structure, which is the one that we want, where we can clearly see the lithium columns. Then there is the intermediate structure, which is similar to the spinel structure, but the lithium columns has been, or the lithium atoms has been replaced by manganese or nickel manganese atoms. So they also forbid the diffusion of the lithium into the cathode material. And then you have the rock-salt structure, where you have only one atomic column of metallic cation, where the lithium should be. And the rock-salt structure is more stable than the intermediate structure, so that's the one that you are likely to have after many cycles. So let's try to image what is the structure of the cathode material. And first, before to try to do some to draw some conclusion from the imaging that we are going to do, let's see how the sample react to the electron beam irradiation before to study the material by itself. We know that when we expose a material to electron beam, we have different degradation mechanisms through different processes. And also we know that we can get different information depending the imaging mode that we are using. And quite important paper in the field of imaging lithium-based material was a science paper published in 2017, where they have shown that we can image lithium metal inside the TEM if we cool down the sample at cryogenic temperature, and they have even been able to have atomically resolve a lithium metal sample, something that was not possible before. So we know that if we take enough care when imaging lithium-based material, we should be able to resolve its pristine structure. So let's try. So we image LNMO material using a stem. On the bottom of the image, you have the total dose used to obtain the left image. So what you have to consider when we do some TEM imaging, before to get such a nice image, you have to tilt your specimen in order that the atomic column are parallel with the incoming direction of the electron beam, which is called to be in zone axis. So first you have to go in zone axis, so you have to tilt at your specimen by using the lowest dose as you can. And when your specimen is in zone axis, you can start to record really nice image. So on the left-hand side, that's the first image, a stem image that was taken after the sample has been aligned to zone axis. And we can also see that there are two structures. On the left-hand side, you can see that in the middle of the diamond, you have some contrast. And so this contrast is typical from the intermediate phase that I have presented before. If you look at the area more inside the particle, more inside the bulk site, you can see that there is no contrast or almost no contrast inside the diamond. So it means that we still have the spinel structure. All right, that's good. So some people have published that the surface of this particle is the intermediate phase, and so that it is due to the cycling of the LNMO particle that has degraded the surface. But then, if we take some images, some consecutive images of the same space, of the same area, we can see that the bulk part has transformed from the initial spinel structure to the roxal structure. So it really means that the electron beams does modify the structure. And then it makes us worry, can we be sure that the surface area of the nanoparticle, the native structure of the surface of the particle, is the intermediate phase, or could it be that this structure in surface has already been degraded and transformed from its pristine phase? There is really no reason to be convinced of that just by doing some such kind of imaging. So then the students come back to the microscope and did some imaging at different doses. So you can see that the dose, like 10 to the 5 electron per angstrom square, it's a relatively low dose for high resolution imaging. And we could see that even at this dose, the bulk part start to be transformed first into the intermediate phase, and then it will transform to the roxal phase. And when we look more inside the particle, we may start with a spinel phase that also get transformed to the intermediate or the roxal phase. So basically, upon electron irradiation, you can transform your initial spinel phase in either intermediate or roxal phase. It's just a matter of dose. And so we cannot be sure what is really the pristine structure of this type of materials. So we say, okay, let's go and try to do imaging or characterization at cryogenic temperature, because we know that at cryogenic temperature, the lithium-based compounds are more stable. So we did some spectroscopy first inside the TEM. So first we did a spectroscopy at the oxygen edge at room temperature, and we can see that when we increase the electron dose from 10 to the 5 electron per angstrom square to 10 to the 7 electron per angstrom square, we can see some variation in the oxygen edge, and mainly a decrease of the intensity of the pre-peak of the oxygen edge, which is really sensitive to the local atomic banding. And similarly, we can also see that the structure of the manganese L line does change upon irradiation. But when we do the same spectroscopic measurements at cryogenic temperature, we can see that the oxygen edge is hardly modified, and similarly for the manganese. So we have some hope that by doing some cryogenic imaging temperature, we should be able to image the pristine structure of the object. So it's what we did on the top side. So you have 3 images taken at room temperature with increasing electron dose, and you can see the transformation from the spinel up to the roxal structure. But when we do the same imaging with the same dose at a lower temperature, we can see that we can keep the spinel structure in most of the places, and except on the top left surface, you can see that the spinel has been transformed into the roxal phase. So with all of these preliminary experiments, which takes almost a year, we have now found the optimal conditions to be able to image this nanoparticle, and we can start to do some systematical study to study the effect of the cycling of the battery materials. Then we look at one nanoparticle when it has been charged. So charged states means no lithium in the cathode material. And we can see that we have a core shell structure. This image has been taken at cryo temperature, I mean with low dose and so on. And we can see that the core of the nanoparticle has no lithium peak, while there is still some lithium into the darker core area. We can also see that the spectra of the manganese spectra, manganese line, are slightly different between the core and the shell, which means that the oxidation state is slightly different in the core and the shell of the material. and the oxygen age is also slightly different. Then we can do such characterization at different state of charge. So we can image the pristine structure, the charge structure, and the discharge. And what you can clearly see on the pristine material, you don't have any core shell structure. It means that we have a homogeneous composition through the cathode material. When we charge the cathode, we can see that only the shell of the cathode gets charged, and the lithium inside the cathode material didn't have time or didn't have the possibility to exit the crystal. So it means that you didn't extract all of the lithium that was stored inside the cathode material, which limit the total capacity that you can get. And then when you discharge it, you can see again that there is a small, like a 2 nanometer shell all around the particle, which is due also to a permanent degradation of the core shell of the LNMO particle. And then when we collect all this data, so we also took some data of nanoparticle of different diameter, and we can see that for smaller nanoparticle, they get fully delithiated. So you don't have any lithium neither in the core or in the shell or inside and outside. There is no core shell structure anymore. And then we can then try understand better how the materials are charged and discharged, and how the diffusion of the lithium happen inside the cathode materials. So this is what we'll try to publish really soon. That's about it for the low temperature imaging of the material. And now I will go towards the operando characterization that we have performed in my lab. So before to go inside the experiments themselves, you have to understand that when we start from a device, usually it's a bulk device, and somehow we have to mount it on the we have to mount it on the TEM support, and then we have to make it electron transparent. And on top of that, when you want to do operando TEM measurements, you have to make sure that you have some electrical contact to your TEM lamella. A TEM lamella is typically an object or that you extract from your bulk material, and the size of the lamella is typically 20 micron width by 10 micron height. And after when the lamella is electron transparent, so at the end of the preparation, it should be less than 200 nanometer thick. And so I had to develop a way to be able to transfer bulk specimen onto a MEMS chip that can later on be used on a TEM holder able of cryogenic temperature imaging and able of biasing. So this is a process that I have developed in the past. Then when the lamella has been transferred on the MEMS chip, we can thin it down to make it electron transparent. And we can also put some electrical contact by connecting the both sides of the lamella to electrically conductive lines using the platinum inside the focus ion beam. And then already quite some time in the past, I've shown that the IV curve that we can obtain for a solar cell is relatively similar to the IV curve that we can obtain for a bulk solar cell. So it means that the electrical contacts are of quite good quality. Let's move on to the study of the ferroelectric material, and I'm going to start with BaTio. So BaTio has different phase depending on the temperature you look at it. So it has a cubic phase, which is antiferroelectric at temperature larger than 120 degrees. And then it has different phases when you go lower and lower in temperature. And depending at the phase you look at, you have different polarization, which are along different crystallographic orientations. And if you look at this type of schematic, so when you are in the cubic phase, the three directions are equivalent. So the overall polarization is null. And when you go in the tetragonal phase, so you have one phase that start to have, so the c-axis, you start to have a c-axis along the you start to have a polarization along the c-axis. Then when you go to the orthorhombic phases, you have two directions that have a polarization. So you end up with a total polarization, which is the sum of the two axes. And when you are in the lowest temperature phase, then you have a polarization along the 111 direction. And it's what we want to study inside the TEM to know how the polarization change from one state to another. On top of that, we also want to do some operando measurements. So we want to see how the ferroelectric domains are influenced by the electric field which is applied across the lamella, and how the motion of the ferroelectric domains is affected by the pinning site. So it's what my colleague at EPFL did quite recently. So she applies some electric field across the MEMS across the BaTio sample, and then she could see that when you apply a small electric field, you have no movement of the ferroelectric domain. So that's the region that she called hard pinning. And when you start to add a larger field, then you start to be able to follow the propagation of the ferroelectric domain. That was done at room temperature. Then she studies different domains orientation at different temperature. So in the tetragonal phase, we have two subdomains, which are called 90-degree domain and 180-degree domain at room temperature. And you can also, from these two types of domain structure, you can extract the polarization vector using a dedicated technique inside the TEM. Now we want to study similar effect, but at of the low temperature phase. Yes, and so one more slide about her work. So she increased slowly the voltage, and you can really see the interaction between the two polarization directions or two domain directions, and you can really see the two domains in blue and red, which are growing, but also that the growth of these two domains is stopped by a perpendicular domain when you apply an electric field. So, as I said before, so we want to study the evolution of the domain structure when we cool down the, when we look at low temperature phase. So we have four colors on this slide. So we start with the high temperature phase, which is a cubic phase, and then we go into the tetragonal phase, where we have the two domain structures, the 90-degree and the 180-degree domain structure. So we clearly see the transition that happen at 360 Kelvin for this specimen. And then the transition from the tetragonal to the orthorhombic phase happen at around 250 Kelvin. And then we increase back the temperature and we found back the tetragonal phase. So we have been able to control the temperature, like with a quite great accuracy of about a few kelvins, which is something that can only be achieved using this type of MEMS-based TEM holder. It won't be possible using conventional TEM, a cryogenic TEM holder. And then we can study the phase transformation by going at a given temperature. So we can see that upon cooling, that's exactly the same area of the sample. Upon cooling at 250 degrees, about half of the sample is in the orthorhombic phase and half of the sample is in the tetragonal phase. And this is because the thickness of the sample is not homogeneous. So the phase transition happens at slightly different temperature depending on the thickness of the specimen. But when we increase back the temperature, we notice an hysteresis. And so we can see that the orthorhombic phase in that case cover a larger portion of the specimen, and we have about a 10 Kelvin difference in the phase transition between the cooling and the heating. And then we can extract some imaging from the series, and we can really follow the evolution of the domain structure at a given place. So it's what we see in this area. We slowly increase the temperature, and we can follow the transformation from the orthorhombic phase on the left-hand side up to the tetragonal phase on the right-hand side. So this was only the effect of the temperature. It was also to get inside how this material reacts. And then, as said previously, we want to combine, we want to see the dynamics of the ferroelectric domain when they are exposed to external electric field. And it's what we are currently doing. So it's really recent result that we got last week or the week before. And we can see that now we are able to apply electric field. And if you follow typically this part of the specimen, you can see that the domain structure evolve when we apply voltage. And we are, so with the direction in which we apply the field, the growth of this domain structure is easier than the growth is in the other direction. So it's why this type of domains become dominant when we apply electric field. That's about it for the BaTio. And now, so we want to study how the domains move from one place to another in the low temperature range. And these are the experiments that we are going to do like in the coming days. So now let's switch to the ferromagnetic structures and the ferromagnetic measurements. So I'm mainly working with a group in NIE, which are working on YAG. And so what they have found that depending on the crystallographic orientation of the YAG, the ferroelectric resonance is different, and it's depending on the crystallographic direction. And first, they wanted to know what is the quality of the interface between the substrate, the GGG substrate, and the YAG film that has been grown on top. So we just did some simple high-resolution TM imaging, and we can see, so image YAG and the substrate and the YAG. We can resolve the structure of both of them, and we can really see that the structure is epitaxial, and we can also measure the roughness of the film. Then we can do such kind of measurements along different crystallographic directions because we want to see the dependence of the magnetization depending on the crystallographic orientation. This is in 110 orientation, and this one is in 111 direction, which give really nice pattern, by the way. So there we have shown that they're able to grow perfectly coherent YG layer on top of GGG. But more than that, now we want to study the distribution of the magnetic field and magnetic domain inside the TEM. And we can do that by looking at the phase variation of the electron beam when the beam goes through the ferromagnetic material. It's something that has been done since some time already. And by using some dedicated technique, in that case, Lorentz TM imaging and electron holography, they can, on the left-hand side, they can map the ferromagnetic domains, and they can see the evolution of the ferromagnetic domain when they are exposed to external magnetic field. And they have also been able to measure the fringing field outside of the specimen for different sample thickness. And yes, so they have shown that we can measure the magnetic domains, the magnetic response of the specimen by using TM techniques. Well, it was known before, but they have shown that it was possible on YAG. So we want to do something similar. So we start with a specimen that was grown by our colleague in NIE. So the white line is a platinum layer. Then below you have a YAG layer. And if you zoom in, so you can see when you go under or over focus, you can see a white line or a dark line, which is domain wall between two different magnetic domains. And then we apply a magnetic field to the specimen inside the TM, and you can see that this white line, so it doesn't move up to 100 millitesla and start to propagate and go down or propagate at the bottom of sample when we apply large magnetic field. All right, nothing fancy. Then we also study how the domain wall depends on the temperature. So by doing so, we can get information on the pinning site on the defect that pin the magnetic layer, and we can see that it's really a jump process. So from the low temperature phase, you have a given magnetic configuration, which jump when you change from around 150 Kelvin, which stay constant up to 220 Kelvin. And again, you have a different magnetic configuration for higher temperature until you lose the magnetic properties. And the same when you cool down the specimen. But more importantly, we wanted to know if we can manipulate the magnetic structure with a spin current, which is of interest for spintronic application. So what we did, we use the platinum layer, which has been deposited on top of the YAG, and we apply a current across the specimen. As the YAG is not conductive, all the current is going through the platinum. So we have a spin current going through the platinum. And while we apply the spin current, we image the magnetic structure. And it's what we did. So this is the initial ferromagnetic domain when we have no current. And by increasing the current density, we can see that we are able to move the magnetic domain downwards at higher current density. So I think it was the first proof, or the first time that people has been able to image the propagation of a magnetic domain when a specimen is exposed to a spin current within the TEM. That was kind of a proof of concept experiment. And now we have moved forward this technique, and we try to better control the propagation of the propagation of the magnetic configuration. So we are studying that on nickel, on a permalloy sample. So what we did, so we start with our MEMS chips, we pattern the MEMS chips, and we made this diamond structure. So we apply a current, so in the horizontal direction of this diamond structure, we take images at different defocus and so on. So we are able to get a magnetic signal, and you can already see that in the middle of this lozenge, you have some bright point, which is a vortex point of the magnetic structure. And then we can extract the magnetic field, and this color wheel gives you the magnetization direction depending on the color. So you can see that the magnetization is going around the vortex at the middle of the lozenge. And then what we want to do, we want to be able to manipulate this magnetic configuration. So on top of this permalloy, so within the permalloy, we pass some electrical current. And so you can see that for low current, for nanoamp, we have a given magnetic configuration. And by increasing the current density, the magnetic configuration can be tuned. And if you follow a given vortex core, so I think we choose this one, I will show. So these are the different vortex core that can be imaged. And then you follow the position of the vortex core by increasing the current through the diamond structure. So this is the position of the vortex core. And you can see a jump of this vortex core when we start to apply higher electrical current. So now we have shown that we can really move the position of the vortex core, and we hope to be able to, that's promising for spintronic application. So now we are continuing working on this type of measurements to get more information. And on this slide, I will stop the presentation, and I would like to thank the different people that have been involved in this project. So mainly Lisa and Joseph that did most of the experiment. They were helped by Aaron, which was in charge of the fabrication of the MEMS, and Patrick and Chris also for the experimental aspect. And I was the collaborator outside of my research groups that with who were able to discuss the idea, and which also provide the sample for the experiments that we have done. So thank you a lot for your attention, and please feel free to ask any question if you have.
Thank you very much, Martial, for this very nice overview of this technique. Very impressive, and can be applied to many things. So yes, if there's any question, I hear some voice. Jesus, yes.
David, yeah. So thank you very much for the talk. I was wondering, have you tried to image some structural defect while applying electric current, like a dislocation?
So dislocations, we have tried before to apply the current. I mean, we do some basic characterization. So there were no dislocation, but in the BaTio typically, so if we talk about the ferroelectric, the pinning site are believed to be the oxygen vacancy site. And to be able to image or to see more or less where the oxygen vacancy sites are, we need to go to really high magnification, or we need to use some spectroscopic technique. And in the case of BaTio, when we increase the electron dose, the ferroelectric domain kind of disappear because we introduce too much charge to the specimen. So in the same time, we cannot do the visualization of the ferroelectric domain and the structural characterization at high resolution scale. So yes, we are limited by this type of aspect in BaTio.
And maybe technical question, if you had a material that could sustain high current densities, current densities either by applying an electric field or besides the electron beam current, so in principle it should be possible.
Yeah. And I know that a group in Limerick is working on another piezoelectric, and in fact they look at the displacements of the oxygen column depending on the polarization, and they are able to map the displacement of the oxygen column and to create polarization map knowing the position of the oxygen columns. So it means that on this, I don't remember which one it is, on this ferroelectric material, you can do high resolution imaging and still keep the polarized state. So yes, it should be possible.
Okay, thank you.
Thank you, Jesus. Other questions? So, Marcel, I have also some question. I'm not expert in this, but so I have three questions somehow. So the first one is when you say at the beginning that you correct some kind of aspherical aberration, does it mean that now the device is somehow Fourier limited or not?
We are still limited by the aberration. We are like 1 order of magnitude limited by the wavelengths of the electrons. So we are getting closer, but we are still limited mainly by the instability of the instrument.
Mechanical instability somehow, right?
And also electrical instability, because all the lens are electromagnetic lens, so everything should be very stable.
I see.
And
okay.
also temperature, in fact, type of instabilities.
I see. My second question is, I mean, when you discussed about charge and discharge of the lithium battery, so you present these different phases, and what I don't understand really is, okay, what I understand first is that so when you send your electron beams, somehow you modify the crystallographic structure, right?
Yes.
And so you say that if you work at cryogenic temperature, this phenomena do not occur. So this, I think, okay, I see, I understand correctly. But what I don't understand is that the electrons which are arriving at a very high energy, right? Few hundred of kilovolts, so it's quite large. So how the temperature can still play a role with respect to this very large energy of the electrons?
Yeah. So there are many points to consider. So one of the aspects is energy transfer to the specimen. It's in the order of, depending on the interactions, but a few electron volts to hundreds of electron volts. So not all the energy is transferred to the specimen, just a fraction of it. That's one thing. And then we have different interaction mechanism between the electrons beam and the sample. So we have different degradation mechanism. So I just want to come back to this one maybe. And so there are some degradation mechanism that have kind of a threshold. They need some threshold energy. Where are they? This one. So we have mainly 3 different degradation mechanisms. So we can indeed change the temperature of the specimen, but that will not, it's not the one. We have some radiolysis effect. So it means that it breaks the bonding between the atoms, and we have the knock-on damage where the high energy electrons just knock out an electrons from the structure. So the knock-on damage is not influenced by the temperature we look at it, but the radiolysis damage there. And so to answer to your question, why the low temperature makes such a difference, but it's really, I mean, what we really avoid at low temperature, we decrease the radiolysis damage. On top of my head, I can't remember exactly what is the explanation. I will have to look for it. So, okay. And typically why, I mean, it's something that you may know, the cryo-TM imaging that people do in biology. And in fact, they got the Nobel Prize in the early 2010 because they all the imaging in biological material is done at cryogenic temperature, and they're able to reconstruct the structure of the protein, because the main degradation mechanism for biological specimens, it's a radiolysis process. So we know that low temperature is really efficient against that.
I see. Okay, and my last question is, I mean, when I mean, the last is quite general. On the last part of your talk, I mean, when you talk about ferromagnetism and this kind of thing, I was wondering, I mean, it will be very cool somehow to have this kind of device where you can also control the spin of the electrons, right? To have, I don't know, I mean, some spins polarize electrons, and then after that, so some kind of spin imaging. I mean, are we very far from this kind of technology right now, or is it something that?
Yes, people have been taught about. I mean, and it's something that is more discussed, and I don't think that's really been tried. But one of the limitations is that, so first you need to have a spin polarized electron source. So that's that seems to be available. But then you have to make sure that the spin of your wave stays the same all across from the emitter up to your specimen. And it seems that the spin gets, I mean, the spin polarization gets lost over tens of centimeters. So when your sample reach, when your electrons reach a sample, they lose most of the spin polarization. But it's something that people are trying. So typically the idea now is to make devices to spin polarize the current near the specimen, and then we don't have this problem of propagation. And yeah, so the spin polarized current will be difficult, but what people are doing now, which is more within range, they tune the phase of the electron. So they try to change the electron phase to in order to probe different state of the sample. So they are not really trying to work with the spin of the electrons, but more with the phase of the wave. That's something that's under development.
Okay, thank you, Marcel. Other questions? Okay, so if not, thank you very much, Marcel, for this nice talks. We learned a lot about this technique. I didn't know so much about that. Thank you very much.
Thank you all for joining.
Thank you.
And have a good day. Bye.
Bye-bye.
Bye. Bon, je m'en vais. Bye.
Bon, Martial, ok. Merci beaucoup.
De rien.
Et Christian est parti aussi. Donc, écoute, on se voit. Je rentre le 2 mars. Je serai là.
Ok, pas de souci.
Ok, merci beaucoup, Martial.
Allez,
C'était super.
salut. Bonne journée.
Ciao.
Au revoir.
Au revoir. Ciao.